Our next speaker is Mr. Atanu Mukherjee. And Mr. Mukherjee is from an Dastur Energy that not everybody maybe who is not in the industry has immediately knows who they are. So he will give a brief introduction, but they play an important role in hydrogen and in hydrogen decarbonization. And they have also good ideas about it. So that's why we were in contact and we've met and we've discussed. And I said, please bring your ideas forward to a wider audience and talk on our conference. And we're very happy that you accepted, Mr. Mukherjee, and the floor is yours.
Thank you, Hans. Thank you for the introduction. I think Dastur Energy is got roots from India, but we are a company based out of Austin, Texas. Our operations in Europe are based out of Düsseldorf, and the Dastur group of companies has been in Europe since 1969. So just for some background. So we have not been in carbon capture space, but we certainly worked with the European companies for a long time, more than half a century. With that, I just want to kind of like talk in this session a little bit about this whole concept of blue hydrogen, hydrogen in general, and its role in decarbonization, especially in the industrial transformation, because we believe that hydrogen has got a big role to play in transforming the industry as we move to net zero, hopefully by 2050. And I think that the different paths to it, and the idea is to be able to figure out what paths makes most sense from a both technology, economics, acceptance, socials, and political perspective. The next slide, please, Liliana, if you will. And so this slide talks about a little bit of DE, and I don't want to advertise out here, I just want to tell you that what we are in. We are a consulting and engineering and technology firm, mostly looking at system design and system engineering and technology development, along with project management. In the space of clean energy, when we say clean energy, our specific focus has got to do with how do we employ something called net negative gasification in producing energy carriers that help in the industrial transformation, like methanol and derivatives like ammonia, and derivatives like hydrogen and derivatives of hydrogen in terms of generation of power. A lot of people have, not talked about it, but we believe that hydrogen has got a big role to play in the power industry, specifically as renewables become more dominant in terms of the load in the grids. And so we work on that too. And obviously we work on carbon engineering in terms of looking at carbon capture, utilization and design. More specifically, like to what Hans mentioned, to a limited degree on exploring possibilities for carbon to value in terms of carbon to methanol. For example, we work with Iceland company, we're working with an Iceland company in terms of figuring out CO2 to methanol in a manner which is economic, hopefully at some point of time. And then I think a lot of the work that we need to do has got to do with CO2 transport and infrastructure, because we believe that infrastructure and transport is going to be the key determining factor in the success of CO2 capture, use, and storage. And I think there's a couple of concepts that you work in Europe, for example, in terms of clusters. But I think, the whole idea of extending the clusters into grids, just like electricity grids, of CO2 trade and CO2 transport is going to be important to get the cost of carbon dioxide to a point which makes a lot of sense in terms of its economics. And obviously we work, in the countries where we work in the United States and in the Middle East to some degree, and India also to some degree, not only on sequestration, but also UR, which again is kind of like not exactly complete utilization of CO2, but it is a derivative utilization of being able to bubble out oil while sequestering the CO2. So those are the areas that we work in with the specific focus on clean energy, which we think is, I think useful for the areas that we work in. The next slide, please. A couple of quick projects, just, so these are the major ones that we're working on right now. One is for ADNOC, Abu Dhabi National Oil Company in the Middle East, where it is about essentially very large scale conversion of waste, right, petroleum waste, into products, and then taking the CO2 out to generate to generate oil from the fields through a process called enhanced oil recovery. And this is a fairly large scale a carbon capture and a gasification project, which is envisioning to capture about 5 million tons of carbon dioxide for injection in the fields, and then of course looking at the derivative in terms of syngas to be utilized for generating hydrogen, generating chemicals like methanol and ammonia, and also power, more of hydrogen heavy IGCC power. There's one more project that you're working on right now on US DOE with a steel company called Cleveland-Cliffs. And I know, unfortunately, recently IMUDN decided not to go forward with carbon capture project, at least right now. But we believe that this is a significant play in the iron and steel industry, which is a major emitter of carbon dioxide. It's a major industrial base across the world to be able to utilize carbon capture and storage, or utilization for that matter, to be able to apply to steel industry, specifically on blast furnace-based steel industry. And so the Cleveland-Cliffs project has got to do with capturing carbon dioxide from 5 million tons per annum, a Burns Harbor plant, and being able to take 3 million tons per annum of carbon dioxide in for sequestration in the Mount Simon Basin in Illinois. And this is right on the FEED stage, and we believe that this is going to have a big impact on the carbon capture for the steel industry around the world. And then, of course, we work in India on Indian Oil Corporation on capture of carbon dioxide, EOR, and then one more company, oil company in India, on creating chemicals from basically petroleum waste, like petcoke, and be able to convert that into useful products while we're looking at CO2 capture and CO2 sequestration in the offshore fields of southern India. So that gives you a flavor of the company, and I'll just kind of like to the next slide and talk a little bit about what some of the principles we have learned, right? What we think are useful, devoid of what people might think and people might kind of conjure about. And so I think the key thing that we think is important to understand is to recognize that CO2 is the main enemy, right? It's not about gas, wind, coal, oil, solar, or nuclear. I think we lose the focus. And so that gives us a perspective, depending upon the country and the region that you work in, depending upon its state of development, what approach should we take, right, in terms of CO2 abatement, CO2 emissions control, and obviously do it in the most effective manner. And so that gives you an idea that we need to have a portfolio-based approach towards CO2 abatement, right, and not get fixated on specific areas of source of the energy. And I think that makes us better understand how we approach the problem. I think like Hans mentioned and Chris mentioned and others mentioned, decarbonizing industrial activity is the key to a net zero world. And I'll tell you why, with some numbers, why it's important. And I think to do that, given the fact that decarbonizing industrial activity will require some form of feedstock to do the conversions, hydrogen seems to be one of the key carriers which will allow you to do that conversion in terms of industrial decarbonization. And I think, we think that, while there have been examples of point-to-point demonstrations and pilots of carbon capture systems in terms of transport and sequestration and carbon capture management, we think that, we need to talk about scale. We need to implement, what we call a GT scale, and this is something we work in the Texas Basin. On GT scale, gigaton scale CO2 management infrastructure. And that, I think, is essential for deep decarbonization of the different sectors, industry being one of the key ones. And because if you're doing it at that scale, a lot of possibilities become imminent in terms of being able to really drive economies of scale, economies of learning, economies of exchange, right? And I think all those factors drive the transport infrastructure to become commoditized and be able to really transport CO2 with a cost structure and at a risk arbitrage, with a risk arbitrage mechanism, which allows the CO2 transport to happen in a seamless manner. And I think, finally, with what we realize, the tautology, or the principle is that this is all fine, but end of the day, depending upon the region of the world that you're working in, economic viability in an energy transition is fundamental. And if you don't pay attention to economic viability, I think energy transition cannot be accelerated. And I think all these points point to one single fundamental principle, which we all know, I think, and it's worth reiterating, is that we do not have time, and energy transition takes decades, right? So we cannot take a single approach. We got to take an optionality of approaches, and we got to figure out how we really accelerate the energy transition with all these different factors. Because as you know, any industrial process, be it carbon capture or generating a different kind of material, takes decades to develop. That's been the case, for many, many decades since industrial revolution. That might change to some degree, but not drastically. And given the fact that we only got probably about 25, 30 years, we need to have a really diversified, bandwagon neutral approach towards rethinking clean energy, in which carbon capture utilization is a cornerstone, and decarbonizing the industry is going to be a significant factor. Next slide, please. And I think this is the thing that I think previous one, Liliana. Yeah. So this one talks a little bit about what I call the 70% emissions challenge, and we know this, I think, is that generally this taken to 3 major countries, major geographic regions: US, China, and the EU 27, the EU, in terms of emissions across different sectors, in terms of percentages, and those talk about industry, electricity, transport, buildings, and agriculture. And if you look at it, the industrial sector is the second bar, is a significant portion of the emissions across all different regions. And this is more so in developing regions. And as we know, CO2 doesn't have borders. It is important to understand how the CO2 portfolio is built out in different countries. So, 23%, 24% in terms of generally, industrial emissions in US, 45% in China. India is again around 35, 36%. EU again, 21%. So unless we address this, we will not be able to get to the decarbonization we're talking about. We will not be able to get to the net zero we're talking about. So renewables in general will target about 30%. That is assuming full electricity being replaced with renewables, which is unlikely. And even if you extend some part of it to industry, it is difficult to decarbonize the industrial sector, which accounts for the majority of the challenge. And therefore, low carbon energy carriers like hydrogen is key, along with carbon capture is going to be key in terms of solving the global and I think specific geographical problem of carbon abatement across all sectors. Next slide. Now it's just a passing mention about what I talked about. It's got to do with hydrogen methanol through natural gas reforming and what we call as net negative gasification, which is a combination of different feedstocks, including biomass, along with what I said earlier, gigaton scale, a very large scale carbon capture management, are the building blocks for enabling the low carbon industry. So I think that's our fundamental principle in terms of what we think needs to happen going forward. And we see that in different forms in different regions. And we think that's going to proceed further as it gathers momentum. Next slide, please. And so I think the way to look at this decarbonization is to look at it from a systems approach, not a specific technology approach, looking at multiple systems across multiple technologies across the entire value chain, along with economics, and the social impact is going to be fundamentally important, right? In terms of creating a broad-based systems approach to a portfolio of options to address the decarbonization challenge. And so we think that clean energy carriers like hydrogen, methanol, ammonia are going to be key. We think, like I said, GT scale carbon capture is going to be key. Reforming and net negative gasification across different parts of the world is going to be key. Obviously complemented with wind and solar at their accelerated penetration, as we think is going to happen, with some degree of hydro. And I think hopefully at some point of time, nuclear, a small modular nuclear in different parts of the world. And I think this is going to take some time to get traction. But we believe that nuclear, certainly at the right cost and the right scale, modular in a modular manner, is going to make a big difference. And I think if you combine these things in a manner which addresses technology, economics, markets, and policy, I think you have got an approach towards decarbonizing in a way which is practical, pragmatic, and again addresses the different constituents, which we think is important from a decarbonization perspective. Next slide, please. And so here's how we think about what we talk about a commercial scale architecture for clean energy transition of the industry, specifically in the industry. And again, I'm not taking things like transport, which is obviously the dominant player in the decarbonization space. But we think the reforming and again, net negative gasification, which includes biomass and blended fuels, which may include coal. And I know a lot of people talk about coal is not the right thing to do, and absolutely right. But the reality is different parts of the world have got different energy sources and different energy constraints. And the question then becomes not to ignore it, but to embrace it in a way which allows you to decarbonize. And so being able to create and take these different fuel sources from biomass down to municipal waste and be able to blend that to be able to gasify that to create syngas and drive three carriers, methanol, hydrogen, and syngas, which drives essentially chemicals, steel, and power. We think is important for driving the industrial transformation in terms of its energy transition. And I think all these have got hydrogen as a fundamental carrier, embedded carrier. So chemicals like for DME or methanol, which can be into automobiles, or for that matter, creation of olefins or plastics of different kinds for methanol is going to be important. Ammonia as a carrier is going to be important. We think that hydrogen-based DRI is going to happen eventually, not right now. I think that we need to have a dual strategy, not a strategy saying that just go to hydrogen-based DRI right away, because the sheer practicality of that begs to be questioned. The demand for hydrogen, the maturity of the technology of hydrogen-based DRI or iron making is still in its development stage. And like I said, that it takes a long time for hydrogen, any technology based on iron steel to develop and grow at scale. It'll take a long time. So you're going to have an option where you take carbon capture, at the same time use hydrogen-based DRI as a development mechanism to drive the iron and steel transformation. And power in terms of hydrogen turbines supporting renewables is going to be important, we think, along with supercritical CO2 turbines. And all these need to be supported using post-combustion or pre-combustion carbon capture to drive the CO2 disposition network, like I talked about before, resulting in EOR storage or conversion to some useful chemicals. Next slide, please. And so what is a hydrogen evolution model? How does it look like, right? And I just want to talk a little bit about it, right? Considerations for what the hydrogen evolution model will look like should hydrogen become a dominant carrier in the different economies from an industrial perspective. And this gives an idea of, we're going to look at competitive emissions intensities. And I've just kind of outlined based on some of the studies that's been done by different parties. This is from the Global CCS Institute, in terms of what is the emission levels on kg of CO2 per kg of H2 across different kinds of production sources. So you've got SMR-based, without CCS, which is at about 9 kgs per kg. You have got SMR with CCS, comes down to 2 to 3 kgs per kg. If you go to ATR, which is the mechanism which we utilize for gas-based H2 conversion, hopefully over time, similar kind of 90% capture, 93% capture will give you 1-2 kgs of emissions. If you go to coal gasification without CCS, is the highest, about 17 kgs, right, per kg of H2. But if you take it down to CCS, comes down to 2 to 3 kgs. And again, it may be valid in certain countries, in certain regions. And if you look at electrolysis today, because you do not have renewable electricity at that scale and that degree, your cost, your emissions would be based on grid-based electricity. And grid-based electricity today in the United States, for example, is at about 0.5 tons of emissions per megawatt hour. Europe is probably about 0.3 or so. If you take US, you're talking about 22 kgs or so, the highest emission for electrolysis-based hydrogen production because of the grid not being decarbonized completely. And if you do electrolysis with 35-40% renewables penetration, still you're talking about 12 kgs, right? So clearly, you need to have a mechanism by which you have electricity available at scale, very large scale, to drive hydrogen transformation. And so that is a key factor which drives how you go towards a hydrogen economy and how you enable the hydrogen market. And then I got net negative gasification, which talks about how much negative CO2 you got if you embrace gasification of blends. And I think some combination of these would essentially give you how to move forward in creating the hydrogen economy in the most economical and societally beneficial way. Next slide, please. And so if you look at it, just again, consideration of hydrogen model from a production cost perspective, today, SMR with CCS and coal gasification, or for that matter, petcoke gasification or blend gasification with CCS is the cheapest. It's about $1.5 to $2 max, right? In fact, coal gasification with CCS goes down to as low as $1.3, right? Depending upon the coal price. On the other hand, obviously, we've got a challenge right now, and it'll drop down in terms of electrolysis-based hydrogen at about, $4 to $8, depending upon the kind of electrolysis you use. And that'll drop over time, but not very significantly unless electricity is available at that cost as a base load at scale. And of course, there's this whole thing on curtailed renewable, which we think is a bad idea, because what you're doing is you're not driving the electrolyzers capacity, and you get max at 10% capacity. The cost of hydrogen produced is very high, at about $18, $20 probably, right? So here's a portfolio that you've got, and you've got to select how you go about the whole thing. The next slide. And this talks a little bit about the blue versus the natural gas, blue versus with coal or petcoke, and I think you see clear differentiators in terms of the components of the cost. Again, remaining at about $1 to $1.3 to $1.5 on the gas-based case, going up like it's happening right now, where gas prices going up, at $8, $10, $11 per MMBTU, may go to $2.5 per MMBTU, in terms of $2.5 per kg of hydrogen should we use CCUS with the current gas price, and same with coal, and coal and petcoke being the cheapest. So again, some considerations to look at from an evolution model, and if you combine this, right, in the next slide, you will see that you've got to look at what is the resource requirement, right? If EU, for example, were to go to 100 NTP of hydrogen, right, by 2050, like the Hydrogen for EU predicts, right? You're talking about significant scale. You're talking about 2 times the EU's consumption of electricity, right? Of 2000, obviously, maybe a little less now. You're talking about a large land mass. Much as people might say, the land mass requirement, right, is significant after taking into consideration all the factors that go into production of renewables. And so here's an example. It's going to take 70% of Germany's land mass. Significant investment, obviously, and this is just an investment in electrolyzers, not on the supply chain. $500 billion US. And on the other hand, you got SMR gas-based hydrogen, which will get you at $1.2 to $1.6 per kg. Similar investment. Infrastructure existing already. And so the question then becomes, what path should you follow, right? So combining costs, resource requirements, emissions, one way to look at it is essentially in the next slide, next slide, I think. How will the hydrogen economy evolve? And so we think the first would be blue hydrogen, which drives 2 things, essentially blue hydrogen driven by gasification of blends and reforming of natural gas, driving power to support the baseload in the fast changing electricity grid, and then of course driving general what we call hydrogen applications like injection in natural gas, steel production over time, oil and gas as usual, refining, and fertilizer and chemicals. And over time, I think heavy transport will develop, because that's when distribution networks come into play, and that will develop. And then this primes the market with electricity, right, to be driven with renewables over time, for basically green hydrogen to come into play and compete with blue hydrogen to create a market which gives you a big scale in terms of combination of blue and green hydrogen to select from at the right economic points for different kinds of applications. And so next slide, please. Yeah, next one. Yeah, one way to look at this is to see how this will develop. And so if you look at the first one, we think is a way to look at it essentially is to look at if I got 1 megawatt of electricity, what is the most effective thing to do? And that's what it tells about on the left-hand bar, that a 1 megawatt out of electricity, the best thing to do is to replace existing coal-fired or gas-fired electricity in the grid, because that's the most effective use of electricity of renewables today, not to produce hydrogen, because you don't have that scale. So if you do that, what you want to do essentially is to enable the blue hydrogen market at scale in the different areas that I talked about, like gas turbines, heavy transportation, hopefully chemicals and iron and steel. And then, can you tap once more, Liliana, if you can, just tap the slide. And then what happens essentially is that as renewable electricity replaces fossil-fired electricity generation, generates cheap green baseload from the grid, that drives green hydrogen, which then competes with blue hydrogen, giving you on the right, essentially, the right combination of blue and green at the right cost structure, right? So I think this is the model that probably is going to evolve, right, over time, and makes more sense to create hydrogen market at scale across different economies and different regions. The next slide, and I think, yeah. And then there's this whole question, that people are talking about, and I know.
Atanu?
Yes?
2 more minutes.
2 minutes? Okay. And I'm happy to talk about this methane leak problem. There's been a lot of this in paper on methane leaks. What happens if you have gas for hydrogen and, and it's going to have methane leaks? Well, there are a lot of issues around that. And I'm happy to talk about it in this slide based on some of the recent work that's been done. The next slide. And then comes the question of how do you handle CO2 at gigaton scale? Right, to do all this, you need to have big handling of CO2 GT scale. Next slide, Lillian, please. And the idea essentially is how do you manage CO2 at GT scale? And one way to look at it in the next slide, Lillian, is to look at this as a federated infrastructure where you separate out the industrial emitters, right, and emitters from the network and the storage. And you essentially drive the network as an entity which has a contract with the emitters and the storers in a way which enables a business model at very large scale and at commodity number of commodity cost. And so this one that we're doing for Texas, which talks about 0.5 GTP of CO2, and then driving about 25 to 30 GT over time, obviously, of storage at 10 to 50 MTP of EOR. And I think CO2 collection, aggregation, transport, and disposition infrastructure that is economically attractive and operationally seamless for emitters is crucial for this whole thing to operate. And finally, I think, next slide, and the next slide. Next slide, please. Yeah, previous one. Quick one. And I think, so this is again the same thing. How do you design it across larger regions? And there's models on international trade that we use to be able to also not only just store and sequester CO2 in one place, but being able to also transport and trade it across different regions, depending upon the competitive advantage of CO2 in different regions. And so there's a lot of factors that come into a model like this. And we think for driving this, anchoring large-scale H2 projects based on, gas-based hydrogen or fossil fuel-based hydrogen is important to drive this kind of CO2 network. And so I think that CO2 commodity infrastructure, along with hydrogen in the way that we think is going to develop, is probably going to be a model for development of hydrogen at scale for the markets around the world, including Europe, I would imagine. Thank you very much. That's all I got to say. And if you have any questions, I'm happy to take that offline or in this, in this session.
Thanks, Atanu. And that was indeed an inspiring presentation. And you have strong ideas on how it could be and how it could work. And your ideas are maybe sometimes raising questions. So I'm checking in the chat if there is any questions at the moment. There are no questions yet. So then there's this question from me. In Europe, there's a lot of NGOs saying we shouldn't do CCS for industry because then they continue to burn oil and gas and we have to get away from that. And that is a line that we don't seem to have a good answer to that because politicians are very sensitive for that element. You've seen in the Netherlands, where I'm from, that, for instance, Tata Steel is now bending away from CCS and moving directly for hydrogen in steel production. What would you say to them?
I think what I would say is that, the reality is that any kind of industrial process transformation takes a lot of time. So you have to keep your options open. While you do hydrogen-based transformation, let's say in Tata Steel and IMODEN, you would have to also look at carbon capture as the mechanism to bridge for the next 15, 20 years to keep the operations open. So I think that is a reality, and that's something that needs to be worked with the government, the political, as well as the society, and a lot of education and knowledge required. Because unfortunately, much as we would like to transform overnight or 5 years and in 10 years' time, that doesn't happen, right? There is a technology issue, there's a stranded cost issue, right? If you look at it, right, you cannot strand 60% of Europe's production, which is based on blast furnace, right, today in steel, and let it go to China, for example, which anyway is going to emit what you call carbon dioxide, and that's going to come and, carbon dioxide doesn't have any borders, right? So I think, it doesn't achieve any purpose. I think you've got to be practical about it, and we've got to look at an optionality where we look at the right set of options and investment in technology for the future, and looking at carbon capture to abate the carbon to be present.
Thank you. And there is one question from the CO2 value organization saying, well, we all agree that CO2 is the key. They would not like to call it the enemy, but more like valorizing or storing CO2. But then the question is, given the climate urgency, don't you believe defossilizing emissions will be absolutely crucial, for example, by supporting and incentivizing industries to use more climate neutral energy? Well, I think you have answered that already a little bit in what you just said. Anything to add to that?
Yeah, I think, you know, we obviously, the first impetus is to look at carriers which allow you to transform the production process itself. But you can only do so much in the near term, next 10 years or 15 years. So you will have carbon dioxide coming out, and obviously sequestration has a cost to it, and so you'll pay the cost. But to the extent that you can take the carbon dioxide and convert it at some scale to value-added products. For example, there's a company called CRI out of Iceland, which does methanol production from CO2. And, you know, it's somewhat feasible depending upon the cost of hydrogen, right? There's applications of concrete curing using CO2 at some scale, right? So I think those are obviously complements, but the fundamental mechanism has got to be other carriers over time, and sequestration, carbon capture along with potentially sequestration as the main engine at scale in the medium term, right, as the solution. And that way you have optionality to be able to give you a direction which makes sense.
Okay. Thank you very much for your presentation with all the technical backgrounds. I think that was very helpful, and thank you for your what's one of the some others in the audience just saying as well, for your realism, and that it's not only about dreaming, we have to do it in real life. So that's really appreciated. And we had 4 panelists, and I must say that we have lost during our conference 2 of them. I got an apology from Johannes at the beginning already, that there was urgent other business that called him away. And I've just learned that Mr. Eekhaas is also unavailable at the moment. One of the risks of being online instead of in a room, because then they can't walk away. But that's reality. So I would like to invite Ms. Marta Lovisolo and Mr. Mukherjee back to the screen. Atunu, are you there?
Yes, can you see me?
I can't see you. Now I can. Yes, I can see you again.
Okay, there you go.
Okay, good. And I'm just checking with the organization. Can we put the 3 faces on the screen for everybody? Yes, there we are. And when we are talking, probably we will be a little bit louder. Thank you very much. Good. So it's a smaller group than expected, but high quality. And I'm first going to Ms. Marta, because you are, Marta Lovisolo, you are the new person in the on the table. Can you please very briefly introduce yourself and your organization?
Yes, thank you for inviting me. Thank you for having me here this afternoon. Good afternoon if you're based in Brussels as well, or good evening or good morning, wherever you are from. So my name is Marta. I work for Bellona Europa, climate NGO. We're based in Oslo, Brussels, Berlin, and the UK. And our main stream of work is on industrial decarbonization. I, in particular, work on hydrogen and renewable energy and energy systems.
Thank you very much for that. Okay, before we go to some of the questions, just quickly to both of you, and first to you, Marta. What have you heard this afternoon that you thought, hey, that's worth remembering? That's something I want to, well, you won't tell it to your kids, but when they want to take home and think this is something to think more about.
I think this question is very interesting, especially in this hydrogen work. We've been talking over the past year more and more about hydrogen, and often people focus so much on hydrogen that they forget the bigger picture. So what is hydrogen for? Why do we need hydrogen? And is hydrogen a useful tool for our climate action? And I think something that we heard this afternoon that was for me particularly interesting is the fact that we, yes, must deploy hydrogen, but hydrogen needs to be coming together with a lot more renewables, and a lot of more renewables need to come on grid to be able to produce green hydrogen. And same goes with blue hydrogen. Blue hydrogen is a possibility, but cannot be seen as a silver bullet solving all problems. So what I liked from this afternoon, different speakers' inputs was this keeping in mind that hydrogen, it's important, it's interesting, it will be useful to decarbonize hard to abate sector, but it remains one part of the solution, and we need to go on with the rest of the solutions as well.
Look at the total package and the real problem at hand. Like Mr. Mukherjee said already in the beginning, that's indeed. And Mr. Mukherjee, for you, did you hear anything that you thought, well, that was really something that good to take home?
Yeah, so I think, pretty much consistent with I think what we have been seeing and thinking and hearing. But I think one thing which particularly stood out on the hydrogen front was kind of reaffirmation by Equinor on the use of hydrogen as a flexible power source, right? Which we kind of like always thought would be really useful because, yes, we should go absolutely full renewables at full blast, but, renewables has got its limitations, and what is the best way to kind of like make renewables reliable in the most effective manner? And it seems to me that, if you have hydrogen as a mechanism for flexible power generation, it really gives the fillip to renewable to be able to generate that kind of electricity baseload to create more hydrogen, and obviously for other sectors of society. So to me, that was, I think, very reassuring.
Thank you. Yes. For this roundtable, I would like to invite all the people, all in the audience, all the participants to put their questions up. I'm not sure if I can take them all. We have prepared a few questions as well for the panelists, but I will go a little bit back and forward between the prepared questions and what we can expect from the and what questions we get from the audience. First, there is a question for the audience, and I think it's for both of you. And I think it's an interesting one. When you produce green hydrogen with an electrolyzer, you produce oxygen. And can we use this oxygen for oxyfuel with easy carbon capture? And we never see that. Is that something that would drive costs down? Would that be an interesting option to combine green hydrogen with oxyfuel combustion? First to Mr. Mukherjee and then Marta.
Yes, absolutely, and I think that's spot on, right? I think a lot of the oxygen generation is discounted in the hydrogen production of green hydrogen, and it certainly can be utilized, right, in terms of not only oxyfuel combustion but other uses, right? Oxygen has got different uses in the industry, especially in the industrial aspect, and so I would imagine that certainly the effective cost of hydrogen, provided the oxygen can be utilized, can certainly be, improving the economics of hydrogen production and hydrogen cost. The thing around oxyfuel combustion is that certainly, yes, that's a possibility, but still the practical aspects of oxyfuel combustion at scale, right, has got some time to go. So I would imagine that, yes, in a limited sense, oxyfuel combustion can be utilized, right? But I think more importantly, industrial settings have got different use of oxygen. Right, and I would imagine that that certainly is something that needs to be accounted for in hydrogen production using electrolysis.
Thank you. And Ms. Lovisola, do you at Bellona speak a lot about oxygen and the reuse of that oxygen?
I must admit, oxygen is not always, let's say, the main topic we end up. But I think this conversation is really interesting in a bigger conversation. We talk a lot about circularity, circular economy, and a big factor of circular economy is being able to always use the byproducts to make more products in an efficient way with less, the least waste of energy possible at all stages. And so I think it's very important whenever a new industry develops, like the hydrogen production industry and the electrolyzer industry, to find, production chains in which the byproduct can end. And I think this will be the development once the industry starts developing a bit further. Today, we're really at the beginning of this industry, so it's normal that we're not focusing on the byproducts yet, but I think this is the movement. This is where things are going, and I'm sure oxygen will have its own downstream once the industry starts developing.
Okay, thank you. Then another technical economical question for the both of you, and that is on, we've been speaking about blue hydrogen and green hydrogen. And what are the key decisive elements for starting with one or the other, or doing one or the other? What are the key elements that decide such a decision? What is best, not on what and what is happening in industry? First, Mr. Mukherjee.
Yeah, so I think I kind of like try to present that in a slide, right? So I think the key goal is to make the market for hydrogen at scale, right? If you look at the use of hydrogen for enabling all these industries, you're talking very large scale of hydrogen production in fairly short span of time, which is economically viable eventually, right? So you got to make the hydrogen, you got to jumpstart the market, right? And so the question is, what options do you have at this point of time? Obviously, you got the renewable option, but at this point of time, renewables are best utilized in decarbonizing the grid, right? Because if you decarbonize the grid, you're going to produce electricity at cost structures which are much more competitive, right? Which are decarbonized and which can be used at scale to support green hydrogen production at a much lower cost structure. So that's going to take some time. So instead of that, what you want to do is start with blue hydrogen simultaneously, which will give you the market opening and the market making in terms of scale of hydrogen production at a cost structure which allows adoption, while at the same time, renewables drive the grid towards more cleanliness or more decarbonized electricity at a cheaper cost, which then eventually drives green hydrogen. And once you get these two components working together at the market will kind of like distribute, right, the hydrogen production depending upon the price and the economics. So I would imagine that it's not either or. You must invest in green hydrogen, but you start what you call the production, start enabling the industries based on blue hydrogen, because that's the most economic. That's the best way to do it at this point of time. And that's, I think, the most practical path, right, which enables also green hydrogen in the future.
Thank you.
So,
and for you?
So I would like to add another element to look at this question. I pretty much align with Mr. Mukherjee's answer, but I would also like to remind here why we're talking about hydrogen. We're talking about hydrogen for climate action. So I think one very important element here to consider, it's what's the climate impact of both the technologies. Both the technologies can have a very positive climate impact, and they both can have problems. And so I think it's very important, whatever the technology that we deploy, that we make sure that the life cycle assessment emissions are as low as possible in both cases. And this, it's very straightforward. With blue hydrogen, we need to make sure upstream emissions of methane are really, really low, close to zero. We must make sure that the carbon capture and storage, it's well done, and carbon, it's actually permanently stored. But this, it's also very important when we talk about green hydrogen. Green hydrogen, it must be produced with green electricity, but green electricity has not been diverted from decarbonizing the grid. Decarbonizing the grid is what we need to do right now. We need to provide more green energy to directly electrify our industry and our economy in general. And if we divert this green electricity, we're increasing emissions elsewhere. So we're not actually doing proper climate action. So green hydrogen is a solution, blue hydrogen is a solution, but both needs to be done properly with very low greenhouse gas emissions.
Okay, then I have immediately a follow-up question for you, because there was a report by Cornell and Stanford universities on the methane co-emissions, and almost saying that blue hydrogen is worse for the climate than gray hydrogen. I mean, I've always calculated that gray hydrogen until 2030 in Europe is worse for the climate than green hydrogen because of the grid. Huh? So everybody is a little bit having this, what do you think about this methane emission factor? And is that impactful, or is this calculating in a wrong way? What is your opinion about that?
Methane can be very impactful. Emissions from methane can be very dangerous, and a very little methane emission has a much bigger impact than CO2 emission, especially in the short term. So blue hydrogen, it's potentially very problematic, can increase emissions, but we can also, we should strive to impose very strict standards that ensure very low methane emission, very high capture rate, permanent storage. Once these standards are in place, based on an LCA analysis, blue hydrogen can be almost zero carbon. And the possibility is there. The standards must be strict. They must be implemented strictly. And then it's up to the gas industry to, deliver on these standards. So if the standards are there, if we comply with them, then blue hydrogen will be very low carbon. If there's no standards, if we don't calculate, we don't account for the methane emission, if we don't really account for the capture, then probably blue hydrogen, it's very dangerous for the climate.
Yes. Mr. Mukherjee, do you have a...
Yeah. So I would like, this may be a little provocative, but I think I would like to question some of the specifics around those papers. So I don't know whether you know or not, there is an unpublished paper which is supposed to come out maybe in a month or two, kind of like questioning the veracity and assumptions that are made in that paper. This is by top scientists from MIT, TH, Zurich, Aberdeen, Sheffield, some of them, I think. But if you look at some of the assumptions, and again, before that, I completely agree with what Marta has just said, right? That you got to put the standards, you got to put the leaks in, absolutely. But if you look at some of the assumptions, 3.5% methane leakage, that's not realistic. If you look at the methane leakage based on EPA in the United States, it's about 1.6%. There might be some errors. There are some errors. It's probably 2%, right? It's probably going to go down with the methane program in terms of standardization and leakage stopping in the upstream significantly. If you look at the leakage of methane in upstream and the supply chain in Norway, for example, it's very little, 0.2 to 0.3%. On the other hand, if you look at the leakage of methane in places like Libya, it's 6%, right? If you look at Qatar, it's 0%. So there's a lot of diversity in terms of the data, right? Pointing towards perhaps decreasing methane leakage, right, over time. And as regulations come in place, right, with OGCI, for example, pushing that, and many other institutes pushing that, your methane leakage doesn't go down. If you look at the equivalence of blue hydrogen and green hydrogen based on this latest paper that is coming out, you will see, which I think is a more nuanced calculation and estimation, you'll see on a life cycle analysis basis, and I think that's been called out earlier, on a life cycle analysis basis, blue hydrogen and green hydrogen, blue hydrogen at a 90%, 92% capture, and blue hydrogen, right, with a methane leakage of 0.3% are equivalent from a CO2 emissions perspective at 2 to 3 kgs per kg of H2. So that's what it is, right? A lot of the data that is collected right now, it's not exactly, we're not exactly clear whether they're accurate or not, because they're collected by satellites, right? They're collected by drones, and they have what we call as temporal and spatial variability, which creates a lot of uncertainty. So I think that making a pronouncement that, blue hydrogen at 3.5% methane emission is a bit of a stretch. And I think that if you look at the same authors, Jacobson and his team, who made this claim in 2015 in the Proceedings of National Academy of Sciences, where they could clear the grid, or they can clean the grid 100% using renewables and hydro, and that was taken down in 2017, where it said it's not possible, and there's basic factual errors, right, in emissions in terms of assumptions and the methods. So I think, although that may not be relevant out here, all I'm saying is that I think there's a lot of factors which play out here, and the industry is anyway pushing towards methane and reduction. And I think if you take all these things into account, I believe that you will have a very strong case for blue hydrogen as a scale producer of hydrogen in the future.
Okay, and thank you for those comments. And because I think if we round the green and blue discussion up, and we say it's both relevant, it really depends on setting good standard. It depends on your timing on the emissions of your grid. In Norway and Sweden, it will be different than in the Netherlands or in Poland. It depends on the time in your development, but it's also a clear call to both the project developers and the EU to make sure that the standards are high so that we don't get any fake solutions, because in the end, that's what we want. We want real solutions. Okay, so far on gray and blue. I got a question for Ms. Levisolo on the EU policies from Trudy Bernier. Can you share your perspective of what you identify as the key elements that should be added, amended, strengthened, changed in the Fit for 55 proposal to boost more carbon capture? So what needs to be done better in the Fit for 55?
So
let me start it, she thinks.
No, it is a wide question, right? Fit for 55, it's over 14 files, and carbon capture potentially has a role to play in all of them. And there's new files that will have to come out soon, like we're all waiting for this gas package to see, blue hydrogen, does it make it, doesn't make it in the gas package. So this is a very wide question, and I'll try to touch upon some of the elements. I think what is would be interesting to boost even further carbon capture, it's the carbon capture and storage is the role it can play within the ETS with the phase out of free allowances. So phasing out free allowances faster, implementing a well-functioning carbon border adjustment mechanism can help us strengthen those industries that want to move toward carbon capture, to decarbonize. I'm thinking about cement industry, I'm thinking about steel making. If we make sure that the free allowances in those sectors decrease faster, and we protect our clean green industry through a carbon border adjustment mechanism that is in place and works well, then I'm sure carbon capture will take off in Europe. Then there's also other part of the system that needs to be strengthened. For instance, we were working on CO2 transport within the 10E files. So within the 10E file, for us, was really important that CO2 transport was included at the different level of the system, because we cannot have storage but not be able to bring the CO2 there. So we need to think about carbon capture also in an infrastructure and systemic way. I do think the EU is moving in that direction, but I also think it's moving too slow. And so we're happy to start seeing some of these details finally coming up in the Fit for 55, but much more can be done and faster.
Okay, thank you. And Mr. Mukherjee, can you give us a little bit of a flavor of what the American government is doing at the moment? Are they similarly pushing for these technology, or are they stronger, or are they slower? Or where are they?
Yeah, so I think, as you would know, that unlike Europe with the ETS system, right, which I think is the right way to go about it. I think that's the absolutely right way in terms of driving the incentives for carbon abatement. The United States is a little gun shy of anything to do with tax, right? And so they have got a mechanism called 45Q, you may have heard, which is basically a credit-based system, which is kind of like a regulation with incentive to drive carbon capture adoption, which works to some degree. But eventually, I think they're moving towards a carbon pricing regime, either based on a tax or based on a cap and trade based system like you have in the US, like in Europe in the ETS. So that's one. The second thing which I think is the US government is driving quite a bit, has got to do with the really enabling the carbon capture infrastructure, which I think I tried to tell a little bit in my presentation. The importance of carbon capture infrastructure at scale, at gigaton scale, at very large scale, it's got massive bearings in terms of enabling, the carbon capture industry, if you would call it, because that's what commoditizes costs. That's what creates seamless movement. That's what creates arbitrage of risk, right? If you have point-to-point solutions, you will not be able to scale carbon capture at gigatons, like was mentioned, 1.4 GT, right? At a minimum, or at a medium in Europe, for example, in the future. So I think a lot of work in the scale infrastructure, right, would be, I think, useful to consider also. Although I do know that the initiatives in Teesside, for example, right, and the Netherlands are good starting points, but those are specific clusters in specific regions. I think you need a much more expansive cluster across, or expansive hub or grid system across the geography, so that you have a more seamless movement at a better scale, better cost structure, better opportunities, and better risk arbitrage. So I think that's what probably needs to be looked at, right, as a part of EU 55, if I may.
Okay. We'll see which of the continents will step to the plate first, but indeed, that's what we need. That is, I think, for most of us, that's obvious. I go to a question that's from the audience, from Jack Shee, and he says, well, CCS, we got positive signals, it looks to be on the way, but what about CO2 utilization or CO2 negative technology? Is that going to fly in the coming years, or does that really need a much higher CO2 price? First to you, Marta.
So CO2 utilization, I think it's a very complex topic from a climate perspective. So when we capture the CO2 and then we use it to produce more fuels that we will burn, eventually that CO2 will go back to the atmosphere as well. So we really need to make sure we don't think that CO2 use, CCU, has the same climate effect as CCS. In CCS, we store CO2 underground and it's going to stay there in a permanent way. While when we use CO2 to make a fuel, we know that fuel will be burned, that CO2 will go back to the atmosphere. So we need to be very careful when we consider from a life cycle analysis perspective, okay, we captured that CO2, but what it's been used for. So there's some uses of CO2, especially CO2 coming from direct air capture, which are very useful, and eventually we will need those offsets to get there, that remaining 10% of 5%, we'll see, of the economy that we cannot decarbonize directly. But we need to be very careful and not thinking that CO2 use will be a panacea solving all our problems, because CO2 use in the end gives back the carbon we captured from the atmosphere. It will push it back in the atmosphere with a lot of energy use in the meantime. So I think my point is it's very important to keep these two conversations very separate and consider what's their climate impact from a complete life cycle analysis perspective.
Okay, so that the first part of the answer, I think we should take it in two, is that CCU, yes, it can be useful, but be careful, don't be blind about it. Same as with blue hydrogen. It must be done well, and you have to calculate the real climate profit. And then the second question is, do we expect a CO2 price coming out of that will be competitive? Do you have any insight in that?
I think for very specific uses of CO2, I think so. I think CO2 prices are going up, will continue to go up, and as we get closer to 2050, 2040, 2050, I think CO2 prices will be high enough for the specific, very unique use of CO2 to be put in place in an economic way. But the reason why they're not competitive today is also because they're not the solution we're looking for today. So I think it's important that we focus on the solutions that we need today to then get to those solutions in a second moment.
Okay, that's always a matter of timing, and you have to start somewhere. So that's fair enough. And Mr. Mukherjee, how do you look at CCU and maybe also at DAC, at direct air capture?
Yeah, so I think I tend to agree with Marta, but with a little bit of a perspective, if you will. I think from a perspective of CO2 use and storage, the first thing that we need to look at is how do you enable the carbon value chain, right? And I think that, utilization and storage are obviously important, right? Although I must say that utilization is a very minuscule portion of the solution, right? Even if you were to convert, right, all the carbon dioxide that's available, right, to produce all chemicals, for example, that would only take 2.5% of the total CO2, right, of the atmosphere, right? That's limited today. So CO2 utilization as such is a very small part of the whole equation. Nonetheless, having said that, there are certain innovative mechanisms by which you can convert CO2 to value. For example, CO2 to methanol is something that's possible, right? Although the cost is very high, given the cost of CO2 and given the price of CO2 as it comes out, you will become probably competitive in CO2 to methanol as a mechanism, right? Similarly, CO2 for concrete curing or direct injection for carbonation, right, or mineral aggregates, where CO2 gets embedded, right, permanently, is something that's quite possible, although in small amounts. That's certainly what you call a possibility. And there are complements, right, to obviously the much larger scale sequestration requirement that's a solution for carbon abatement through capture mechanism. So I think that's my take on the CO2 to value, CO2 conversion to value, and I think that's important, and it's a complement. On the other hand, direct air capture is an interesting mechanism, which is pretty much in its infancy at this point of time. And the basic physics of direct air capture, just prices it out in terms of, the CO2 price of capture or from any CO2 price abatement mechanism. Today, for example, CO2 capture through direct air capture mechanisms is at about $600 per ton. Right? It may go down to $350, $400 per ton. There are a lot of claims around that. People say it may go to $100, but that's highly unlikely given the basic physics and thermodynamics of direct air capture, right? Because the concentration is so low, the amount of work required is so high, you can only go so much. Second thing is in direct air capture, given the low concentrations of CO2 in the air, and given the vast amounts of air you're going to process, the amount of space that you require for air to flow through is going to be significant, right? So unless those two challenges are kind of like overcome over time, and I'm sure, there'll be solutions to that, direct air capture can certainly be a complement, right? Over time, I think much longer period of time onto vertical carbon capture systems. I would although say that net negative technologies like biomass gasification, for example, to create biofuels, would be probably a much better complement towards a 10% issue that we have got on carbon capture. So I would imagine that over time, blended fuels, which have got significant amount of biomass, can address this problem of 10% out in the air more effectively than probably other mechanisms.
Answering in one go also the question from Adam on the remaining 10%. Yeah, well, as a comment from my side, I've seen that, especially, for instance, for the production of kerosene, synthetic fuels may have a role to play in the total picture. But indeed, you have to look what are the alternatives, are there alternatives, and per technology you have to see. And if you can use, for instance, hydrogen directly in transport, then the question of making first methanol is becoming like, is that an added value or not? And that depends on how storage will develop. And for a lot of the estimations of large-scale CCU, I'm not talking about the specialties, but the large scale, depend on the alternative availability of storage options for electricity. Because we do all agree that we do need flexibility and storage capacity for our overflow of intermittent renewables. And I think today, no one knows what storage solution is going to be the winning bet. And especially, for instance, in Germany, but also in other places, there are quite a few professionals and very well-informed professionals who bet on CCU fuels being one of those storage options. I don't have I can't predict it, but I don't want to disregard it either. But as long as, and that's I think what you both are saying, if you look at it with an open mind and with the goal, the end goal in the back of your head, and that is the climate gains for a low price. It's expensive anyway, but as low as possible, because it's already so expensive. But the climate goal is what we should have in the back of our minds. And Marta, there is an invitation from Thierry Bernier from the CCU to have an offline discussion a bit more extensively on CCU and CO2 valuation. Okay, we'll take that one offline. Okay, guys, I think we're coming closely to the end of our meeting, and I want to give both the two remaining speakers in the panel the chance to give, let's say, a last message to the audience. What should they look at? What is the future? Where is it coming from? What angle do we need to take where we are now? What is, if you had 1 minute to share with the president of the European Commission or with the United States, what would you tell him to do now on this field? Mukherjee, you're first.
Okay. Yes. So I think, yes, the future development and the pathways, right, are uncertain, as usual, as it happens in any of these situations. And so the different technology pathways, and we shouldn't, first of all, we shouldn't lock ourselves into a specific pathway. So I think the first thing is to really keep the options open and invest in options. The question then becomes, how do you invest in options, and what's a rational model for investing in the options which make sense so that you can hedge the uncertainty in the most economically effective way in the future? I think if we can design a mental model, a thinking model around that, rather than saying that, push for renewables or push for vertical hydrogen or push for, XYZ, that's a more rational approach, right? Which will benefit the society, benefit the economies in a much better manner, I would imagine. And so I think keep our minds open, keep the optionalities open, look at rational mechanisms of investments in different areas so that the economic advantage that you get over a period of time is maximized.
Okay, so you go to Biden and say, keep your options open and don't bet too quickly on one horse. And Marta, what are you going to say to Mr. Timmermans or...
So keep your option opens, but keep the climate in mind. Remember to set very strict standards, whatever you're doing. And because, we can be lying a bit to ourselves, pretending that accounting tricks will make our hydrogen green, blue, hydrogen zero emissions, but we cannot definitely lie to the atmosphere. So the amount of carbon, the amount of greenhouse gas emissions we're putting out there, it's not going to change if we change the accounting rules. So we need to make sure that we account for greenhouse gas emission properly. The accounting today is key. Hydrogen is still a marginal sector, but it's developing, and we will develop more and more and more. And if we don't get it right today, we risk having big emissions tomorrow. Hydrogen might transform from our climate solution for yet another climate problem we need to tackle in 10 years. So be careful now, set strict standards and make them respected.
That's a clear message. And with those wise words from Atanu and from Marta, I want to close this meeting. I want to thank the participants who stick with us. I hope you've enjoyed it. I hope you've learned something. I hope you're stimulated. I have been. I want to thank Marta and Atanu for their excellent contributions and knowledge. Also the other speakers who unfortunately had to leave already. I think that we cover the field in both an climate ambitious way, as well in a technical rational way. And I like that combination. There is a lot to do, and we can't waste too much time in talking nonsense. So I really appreciated all the inputs, all the very relevant and good questions from the audience. Thank you very much. Thanks, Liliana Guerrera, for the presentation, my colleague at Trinomics, who did all the organization behind the screen. Thank you very much, Lily, for that. And enjoy the rest of your day. Bye-bye, everybody.
Thank you, Hans. Thank you very much.
Thank you, Hans, and have a good day.
Bye. Thank you. Bye.
Thank you very much. Have a good day.